Because now we move on to another concept we call degree of freedom. We represent by symbol F. What is degree of freedom? Degree of freedom is an independent mode of motion or an independent way in which a gas molecule can acquire or store energy. In other words, means degree of freedom is the numbers of independent way in which a gas molecule or atom can exhibit motion. So, what type of motion they might have, and then through that kind of motion, the gas molecule can store energy. Alright, so let us see what type of motion we might have for a gas molecule.
Degrees of freedom or freedom. They are 1. Degrees of freedom of translation motion, F2. 2. Degrees of freedom of rotation motion, F1. 3. Degrees of freedom of vibration motion, degrees of freedom of translation motion, F. These are due to translation motion of molecule. Maximum number of translation degrees of freedom is irrespective of that the molecule may be monatomic or monatomic, linear or non-linear. It represents at ordinary temperature. Degrees of freedom of rotational motion, F1. These are due to rotational motion of a molecule about its axis of center of mass of the molecule. The number depends upon the structure of molecule. They will also present at ordinary temperature. Degrees of freedom of vibrational motion, F2. These are due to the vibrational motion of molecules about its equilibrium. The number depends upon the structure of the molecule. These are used only at high temperature.
So class, through the video we can see obviously there are 3 types of orientation mode in molecules, whereby we have translational, linear, second one rotational, and the third one vibrational. But anyhow, the vibrational mode of motion can only be present at a very high temperature above 1000 Kelvin. So at ordinary temperature, at ordinary absolute temperature, we might only have translational, or we call it as linear motion, and also rotational motion. So all these type of motion will contribute to what we call degree of freedom of a gas molecule, how the gas molecule might store or acquire energy. So numbers of degree of freedom depends on whether the molecule is a monoatomic, diatomic or polyatomic. So for different type of gases, they might have different numbers of degree of freedom. So it depends on whether the gas is considered as monoatomic, for example helium, or diatomic, for example oxygens, or polyatomic gas, for example carbon dioxide. So mono means we only have one atoms. Diatomic means it consists of combinations of 2 atoms. The gas that consists of 3 atoms or more than 3 atoms, we consider it as polyatomic gas. Alright. So now let us see how many degree of freedom we might have for monoatomic gas, diatomic gas, and polyatomic gas. So class, for monoatomic gas, the gas can move linearly along X, Y, and Z axis. So they are going to have 3 degrees of freedom of translational motions. There will be no rotational motions for monoatomic gas. So when we total up, so for monoatomic gas, they are going to have 3 degrees of freedom, whereby they can acquire or store energy. Then what about diatomic gases, for example like hydrogen gas, oxygens, or nitrogen gas? So for diatomic gas, they might have linear or translational motion along x-axis, y-axis, and also z-axis. So they are going to have 3 degrees of freedom for translational motions. And then beside that, they might rotate for the 2 axes, so they might have 2 degrees of freedom for the rotational motions. So when we total up, for diatomic gas, they are going to have 5 degrees of freedoms, whereby they can store or acquire energy. Then the last one, for polyatomic gas, for example, the H2O, CO2, NH3. For polyatomic gases, they have 3 degrees of freedom for translational motions. Besides that, they are going to have 3 degrees of freedom for rotational motions. So when we total up, they are going to have total of 6 degrees of freedom for polyatomic gas in order to acquire or store energy. So how each degree of freedom might store energy? So we refer to the principle of equipartitions of energy. According to the principle of equipartitions of energy, it states that the average or mean kinetic energy that's stored in each or every degree of freedom of a molecule is equal to 1 over 2 kT. It means that for 1 degree of freedom, for each degree of freedom, the gas molecule will acquire or they can store energy of how much? 1 over 2 kT. Okay, 1 over 2 kT. I repeat. So, let us see one by one for monoatomic gas. So, for the translational motion along z-axis, they are going to store energy of half kT. Along y-axis, they are going to have energy of half kT. And along the x-axis, they are going to have energy of half kT. So total up 3 of these, we are going to have how many? 3 over 2 kT. So this is the total kinetic energy that a monoatomic gas can store or can gain through the motion. So this is the total kinetic energy that a monoatomic gas might have. Alright. Then what about diatomic gas? So for diatomic gas, because they are going to have half kT for the translational motion along z-axis, half kT for the translational motion along y-axis, and half kT for translational motion along x-axis. Besides that, they have 2 rotational motion. So each one contribute half kT. So when we total up the kinetic energy contribute by each of the degree of freedom. So we are going to have 5 over 2 kT. 1, 2, 3, 4, 5. 5 over 2 kT for diatomic gas. What about polyatomic gas? So for polyatomic gas, they have 3 degrees of freedom for translational motion. So they have 1 over 2 kT, 1 over 2 kT, 1 over 2 kT. Besides that, for rotational motion, they also have 3 degrees of freedom. So they have half kT, half kT, half kT for each degree of freedom in the rotational motion. So when we total up 1, 2, 3, 4, 5, 6. They are going to have 6 over 2 kT of total kinetic energy. So this is the total kinetic energy the gas molecule might store or acquire through the degree of freedom they might have. So I conclude it here. So if we apply the principle of equipartition of energy above, we will find out that the average molecular kinetic energy for monoatomic gas will be 3 over 2 kT. Why? Because they have 3 degrees of freedom. For diatomic gas, they are going to have 5 over 2 kT because they have 5 degrees of freedom. Polyatomic gas, because it has 6 degrees of freedom, each degree of freedom contribute half kT. So total up, they are going to have 6 over 2 kT. So 6 over 2 kT also actually equivalent to 3 kT lah, because 6 divided by 2 is 3. So in generally, so I put it in general. So for a gas with F degree of freedom, we will find out that the average kinetic energy per molecule can be expressed as F over 2 kT. So this is the formula to calculate the average kinetic energy per molecule, and it is very obviously the average kinetic energy per molecule is depends on the degree of freedom, and this degree of freedom is depends on the type of molecule. Then class, we move on to the last one. We have what we call internal energy of gas. So gas is in motions, so gas can have internal energy. So class, the internal energy of a gas is the total of the kinetic energy and the potential energy of all molecules of gases. Then the potential energy is associated with the forces that exist between the gas molecule. Anyhow, if we recall the assumption we have for the theory kinetic of gases, we see that for ideal gas, the intermolecular forces are assumed to be negligible. We assume that there will be no intermolecular forces between the gas molecule. There will be no attraction force between the gas molecule. There will be no repulsion force between the molecule of the gases. So, if there will be no intermolecular forces between the gas molecule, then we might conclude that the potential energy of the molecule can be negated. So we can ignore the potential energy that exists for the gas molecule. So the internal energy of an ideal gas will be simply the summation of average kinetic energy of its molecule. Why? Because the potential energy is 0. We can ignore this one. So if we ignore this one, so our internal energy of the gases will come from the total kinetic energy of the gases. Alright, so we know that the average kinetic energy of a molecule is K equal to F over 2 kT. So if there are n numbers of molecules in ideal gas, their internal energy will be simply the numbers of molecule n multiplied with the average kinetic energy for a molecule gas lah. So I will going to have this one. The internal energy of gas will be given by F over 2 n kT. Internal energy of gas. So this is the formula to determine the internal energy of gas. Then since that the Boltzmann constant is R over Na, so when I put it into the equation, I replace the K with R over Na, then I will know that N over Na is numbers of moles, so I will have another equation to calculate the internal energy of the gas molecule, whereby I'm going to have U equal to F over 2 nRT. So bear in mind, F represents the degree of freedom, and this degree of freedom depends on the type of gas. Small n represent the numbers of mole, capital N represent the numbers of molecule, K is the Boltzmann constant, and the capital R is the molar gas constant. So from the equation we get, the result will imply that the internal energy of an ideal gas depends on the temperature. You can see very clearly for a gas, the internal energy depends on the temperature, the absolute temperature for a gas. So if you refer to this equation, it is very obviously our internal energy is proportional to the temperature. So it means that when the temperature increases, the internal energy of the gases will also increase. So if the internal energy of the gases decrease, it will telling us that the temperature is dropped. Okay, so it means that if the internal energy of the gases reduces, then how we know the internal energy of the gas is reduced? When you will find out that it relates with temperature, so it means that the temperature will drop. So remember, As the temperature change, when we change temperature, actually the internal energy of the gas will change. Okay. So class, remember, so our internal energy depends on the temperature. When we change the temperature, then we understood the internal energy of the gas will change. And this concept is very important, and we are going to apply it for our next topic, topic 14, thermodynamics. Okay. So this is all the concept we have for topic 13. So let us try our tutorial 13. We might use the concept we learned in these two videos and try to attempt question 8 and also 15.